So good afternoon to everyone. I'm glad that you have joined this lecture, and actually I suggest that in the next month the entrance to Meet would be available for the people who have their QR codes and they have attached them to their pass. So I hope to see somebody in the auditorium, though it's all retranslated into the Zoom, but maybe it would be more convenient for us to discuss something offline. But today the lecture is called The Power of Boltzmann Equation. I actually would like to show its power to not only to cover the electrical conductivity, but also some other phenomena, because the course of semiconductor physics is actually about the conductivity of semiconductors, but not only about it. And some other phenomena like diffusion and thermoelectricity can be also addressed with the kinetic equation. I hope today it would be more understandable than previous times, and I hope to hear some questions from you. So the scheme of the lecture is the following. First, we will refresh our knowledge about conductivity in degenerate and non-degenerate semiconductors. I will try to sketch it quickly because you already learned about it. This is just repetition of computational scheme, how we solve the kinetic equation to evaluate the conductivity and its dependence on carrier density and maybe some other quantities. Then we will see how to treat conductivity and diffusion on equal footings. How can we do this with kinetic equation? And last, what we will cover today is the consideration of thermoelectricity, thermoelectric coefficients. How does the electric or diffusive current form itself in semiconductors that are subjected to temperature difference between hot and cold ends? So we have learned that the kinetic equation has the following form: the derivative of distribution function with respect to time plus velocity multiplied by derivative with respect to space plus force multiplied by derivative of equilibrium distribution function with respect to momentum, it all equals the collision integral. Could you focus? Можно сфокусироваться на доску еще больше, потому что сейчас на формулки будем смотреть. Прямо вот в размер слайда желательно, а меня можно не показывать. Хорошо. Okay, and the collision integral in most situations, except for the situation of inelastic scattering, can be written in the momentum relaxation time form. So typically we will be interested in the phenomena when the electric field is uniform, and therefore we will drop the terms that have the spatial derivative in itself. Typically it is dropped, but we will see further some situations where they shouldn't be dropped. When we want to evaluate the time-dependent conductivity, like in the high-frequency fields, we should retain this time-dependent term, and it can be, it would be also retained in some other parts of our course when we will consider the optical properties of semiconductors. But for a while, we will also neglect this time-dependent term. And what is retained to get the DC conductivity of semiconductor is the force term and collision term. There are only two terms in the kinetic equation that should be retained. But with this approximation, the kinetic equation is readily solved. We just express the distribution function delta F, it equals the force term multiplied by momentum relaxation time tau p. And there can be different situations when momentum relaxation time tau p depends on momentum itself. In most general form, typically, It can be presented as some constant tau 0 multiplied by momentum to some power alpha. To make this constant have proper dimensionality, we can divide the momentum to some Fermi or thermal momentum to the same power. And this power alpha actually can be quite different. We have already shown that, for example, for electrons interacting with phonons, this power for graphene equals minus unity. It means that the higher is the momentum, the shorter is the momentum relaxation time. High energy electron has higher chance to meet the phonon and to relax its momentum, to get collided. The same actually is valid for bulk silicon. Electrons in bulk silicon interacting with acoustic phonons have the same power in the power law dependence of tau versus momentum. For electrons in graphene interacting with charge impurities, this power equals unity. It means that high energy electrons almost do not collide with impurities. Actually, it can be also intuitively understood that if you have a particle with small velocity, it can get attracted by a charged center quite effectively. There is a long time of interaction between slow particle and impurity that attracts it. But when the particle has high energy, the time of interaction is relatively short, and therefore the scattering is not so efficient. And in one part of our lectures, we have shown how, if we know the solution for the distribution function, we can already find the conductivity. Let me refresh it. Извините, а можете показать еще раз, как активировать перо, чтобы рисовать? Вот, нашел. So if we know the solution for the distribution function, delta distribution function equals minus electric force, but electric force is nothing but elementary charge multiplied by electric field multiplied by tau p and multiplied by derivative of equilibrium distribution function with respect to energy and multiplied by the electron velocity. Well, just to check whether you listened carefully during the previous lecture, why when we solve the kinetic equation, we can retain the zero-order distribution function, equilibrium function, in the force term, but we write the correction to the distribution function in the collision term. Does anybody remember this argument? Because when we wrote the kinetic equation from the very beginning, everywhere we had the same distribution function f that should be looked for, but now there is some strange thing happening. Here we have the equilibrium distribution function, the Fermi function, and here we have the small correction delta f to the distribution function that is induced by electric field. Why we do in the following way? Nobody remembers. Please, somebody, any opinions? Они могут, the sound is on for them? Okay. Well, if nobody remember, then I will refresh this. Generally, the distribution function can be presented as equilibrium part plus correction to this function introduced by electric field. And this equilibrium distribution function doesn't know about electric field, so it is proportional to electric field to the power 0, while the correction is proportional to the electric field to the power 1. And when we solve the kinetic equation, we collect the terms having the same power in electric field. And this term has the first power in electric field due to this force already. So here under the derivative we retain the equilibrium part of distribution function. But the collision term doesn't have this force, and therefore we should take the first power of electric field from the distribution function. If we do some if we retain some other term, the powers of electric field would be different, which would contradict the power law expansion of our solution in terms of electric field. So after we know this solution, we introduce it into the general expression for the electric current density. Electric current density is the degeneracy factor of electron multiplied by sum over all momenta, individual electron velocity multiplied by the distribution function. And the only remaining thing is to evaluate the emerging integrals. I hope that till the end of the course you will be familiar with the general procedure how to do it. Actually, the sum over momenta is the integral over the phase space, which can be written in a different fashion depending on the dimensionality. So if we deal with the three-dimensional space, we write its element in the polar coordinates. The polar coordinates are introduced in such a way that electric field is directed along the z-axis. It's directed along the z-axis. X and y coordinates are orthogonal to it, and when we consider the individual momentum vector for the electron, it makes some angle theta with respect to the z-axis. Therefore, we write it in the way 2 pi momentum squared multiplied by sine of theta, d theta, delta momentum. When we do it in two-dimensional space, we use simple polar coordinates. If we do it in one-dimensional space, then it is just delta momentum with respect to z-axis. Actually, it's instructive that the momentum integral of this equation can be taken in a very abstract form, independent on the dimensionality that we are dealing with. It is best seen on the example of 2 dimensions. Well, if we we can first make the averaging of this vectorial expression with respect to the angles, and then consider only the isotropic part of integration of the isotropic part with respect to momentum modulus. If we try to average the expression of velocity multiplied by the scalar product of electric field and velocity in 2 dimensions, then it is equivalent to averaging of cosine square over all possible angles. The average of squared cosine is 1/2, and angular averaging in 2 dimensions in this expression is equivalent to dividing it by 2. And after we have divided it by 2, we can evaluate only the momentum integral of some isotropic function. And it is quite interesting that if you want to find to make the averaging of the expression in 3 dimensions, you just divide it by the full solid angle of 4 pi and take the integral from 0 to pi of velocity multiplied by velocity and electric field over sine theta delta theta, and actually it is equivalent to averaging of cosine square over all solid angles. And this average is also computed very easily, and it equals 1/3. So it would give us electric field multiplied by velocity squared divided by 3. And this rule is very general. If you want to find the average value of the distribution function created by electric field and average over velocities, when you make this averaging, you should divide by the dimensionality of space. The dimensionality actually of the sample that you are working with. If it is graphene, you divide it by 2. If it is bulk silicon or bulk gallium arsenide, you divide it by 3. And this rule is very general. It can be proven for abstract dimension. Unfortunately, our dimensions are limited to 3 only. So after we did this averaging, the evaluation of conductivity becomes equivalent to evaluation of a very simple isotropic integral. Squared velocity of charged carrier, either electron or hole, momentum, relaxation time, derivative of distribution function with respect to energy, and the element of the phase space, which can now be taken as isotropic one. So in 3 dimensions, it is just a volume of the spherical shell. In 2 dimensions, it is equivalent to the area of the ring, which is located between momentum and momentum plus delta momentum. And in 1 dimension, it is just 2 moduli of the momentum. There are 2 tricks how can we evaluate this type of integrals. It depends on whether we deal with degenerate semiconductor or non-degenerate semiconductor. And it actually shows us how should we consider this derivative of distribution function. We can cover 2 examples. I will sketch them briefly because we already considered them. The first example, if we consider bulk non-degenerate semiconductors. In the non-degenerate semiconductor, the distribution function F0 is a simple Boltzmann function. And it is just a simple exponent of minus energy reckoned from the Fermi level for electrons divided by kT. The beauty of this exponent is that the derivative of exponent is the exponent itself divided by kT, is minus F0 divided by kT. And all the integrals with exponential function and power law functions are evaluated easily with the help of reference books or with the help of Wolfram Mathematica software, and it can be treated quite in a simple way. So we can simplify this by simplifying the derivative of distribution function with respect to energy and rewriting it as a simple exponential divided by kT. And the only thing that we should do, the only extra thing that you should do, you should pass from integration over momenta to the integration over the energies using a very simple familiar rule that momentum is the square root of two masses multiplied by the energy. So the remainder is evaluated very simply, and you get some explicit formula for the conductivity expressed through temperature and quasi-Fermi level EF. Actually, it is not very instructive to get the expressions for the conductivity expressed through the Fermi energies, and to get rid of this, you should express the carrier density in terms of the same quantity, in terms of the Fermi level. You can do this. It is simple statistical formula. You just average the equilibrium distribution function over momentum space, and you get that the fact that the carrier density is proportional to the same exponent of Fermi energy divided by kT. So you can divide these expressions, sigma and carrier density, by each other and get quite a simple formula for the DC conductivity. The result is shown in the bottom part of my slide. You actually get the Drude formula, but probably with some numerical prefactor. So you get the carrier density multiplied by elementary charge multiplied by tau 0, which is the momentum relaxation time evaluated at characteristic thermal momentum, divided by mass, and probably some correction factor. You shouldn't get surprised when you evaluate the conductivity with some exact Boltzmann consideration and don't get exactly the Drude formula, NE squared T divided by M. Because this is because what entered the Drude formula is the properly averaged momentum relaxation time. This proper averaging is shown in my figure. You should actually average the momentum dependent relaxation time tau p, which is for acoustic phonons shown with the red line, and you should average it being multiplied by squared velocity and derivative of distribution function with respect to energy. So you should multiply it by velocity squared, this is the green line, and average it over df0 over dE, which is the decaying exponential. It is not surprising that by this averaging you can get any numerical prefactor that you don't know a priori. It should be derived in each situation individually. So this is how we treat the conductivity in non-degenerate semiconductors when the distribution function in equilibrium is looking like a Boltzmann function. Quite a different situation appears when we deal with degenerately doped semiconductors. Here I will cover the example of graphene, which may look somewhat new for you, but it is doable. Let's try to evaluate the conductivity of graphene when electrons scatter the charged impurities. We have already shown in some of the previous lecture when we dealt with the charged impurities that the momentum relaxation time due to electron impurity scattering is proportional to momentum itself. This again comes from the argument about prolonged relaxation, prolonged interaction for small velocity particles. If the particle has a small velocity, it moves slowly near the impurity, so it takes quite a long time to interact with it. The interaction time is roughly the screening radius of the impurity multiplied by the velocity. When the velocity is high, the interaction time is small, and the scattering becomes less probable. So the momentum relaxation time is longer when the particles are fast. It means long momentum relaxation time means that the scattering is unlikely. Scattering is hardly probable. So to evaluate the conductivity of graphene, or to find its dependence on Fermi momentum, to find its dependence on carrier density, we should just evaluate this integral, or this integral comes from averaging of field-induced distribution function over the phase space with the following dependence on momentum relaxation time on momentum itself. Here I just postulate the fact, but it is almost apparent that graphene is a semiconductor that is almost always in degenerate situation because it doesn't have a band gap. Its dependence of electron energy on momentum had the shape of the cone. So its energy depends on momentum in a linear fashion, plus minus momentum multiplied by a constant velocity, which I denote as V0. And it is, if it doesn't have a band gap, it is natural that the Fermi level always lies either in the conduction band or in the valence band. There is no situation that the Fermi level is in the gap because there is no gap. So it is almost always degenerately doped. It almost always looks like a metal, except for pathological situation when the Fermi level is exactly between conduction and valence bands. So here we should make slightly different tricks compared to the silicon. We should handle the derivative of distribution function with respect to energy in a different fashion, and we should make a different transfer from momentum to energy, because the energy momentum relation is linear, but the transfer from momentum to energy is quite trivial if we just replace momentum by energy divided by characteristic velocity, and delta momentum is delta energy divided by this characteristic velocity. What about distribution function? We approximate it in a different way. If the distribution function is looking like a Fermi function, then it looks like a step with the cusp at the Fermi energy, and its derivative looks like an minus delta function, because this derivative is non-zero only in a narrow region in the vicinity of Fermi level. So the evaluation of conductivity becomes quite trivial, because the integral of anything with delta function is just the function being averaged. So the result is very simple. If we take the delta at zero with respect to energy as a delta function, we should take the remainder on the Fermi level, and the result is simple. We should take the momentum relaxation time at the Fermi level, and we get one Fermi momentum from the density of states, from the forward prefactor. Now, if we inspect it more carefully, we see that tau is a linear function of momentum, and there is one more linear function of Fermi momentum in the prefactor. That means Now it is, now we want to express it via the carrier density. We want to restore something like Drude formula for graphene. Expression for the carrier density is very trivial. If the Fermi function is a step, we just integrate from 0 to Fermi momentum, the degeneracy factor, and the element of the momentum space divided by 2ph cubed. And the result is very simple. It is the degeneracy factor multiplied by Fermi wave vector squared divided by 4 pi. Sorry, the power of 2 is here because we deal with a two-dimensional sample. So we get the fact that the conductivity is directly proportional to the carrier density. It is proportional to the carrier density n, and it actually can be presented as mobility multiplied by elementary charge multiplied by the carrier density, where the mobility is independent of Fermi energy and Fermi momentum. The mobility is independent on Pf. This theory can be compared with the experimental data on the conductivity of graphene. We have sketched in one of our previous lectures that we control the carrier density in graphene just by attracting electrons with the electrostatic potential applied to the metal gates, and this theory where mobility is constant can be compared to the experimental data. You can measure the conductivity with respect to attracting electric potential at the metal gate, which is actually proportional to the carrier density. It equals the elementary charge divided by carrier density and divided by the capacitance of the structure between graphene and the metal gate. And the conductivity is, as expected, a linear function of carrier density. Well, it's almost linear. In some samples it can behave differently, but well, it is very good approximated by a linear function. And the mobility of graphene limited by scattering by charged impurities is a constant that doesn't depend on Fermi energy and on the carrier density. With this, I would like to finish the conductivity parts of my lectures. Please ask any questions either on maths or on physics or on anything else. Don't be shy.
In the previous slide, density of states for graphene was plotted, and I didn't quite get how did we get it? The density of states and is the green line in the plot, and then why is it linear?
Yes, it is quite simple. So the density of states is the number of states per unit energy interval. So it is the element of the phase space multiplied by degeneracy divided by 2ph squared divided by energy interval. So by dividing delta momentum and delta energy by each other, we get nothing but 1 divided by characteristic velocity, and the remaining momentum is the energy divided by characteristic velocity. So the result is 2 pi g energy divided by 2 pi h characteristic velocity all squared. C, it is a linear function of energy. What is your remaining question?
I got it.
Oh yes, you got it, and you see that this P Fermi in the conductivity comes from the density of states. So this part, if it is expressed through energy, it yields the density of states, and a part of dependence of sigma on P Fermi comes from the density of states. Any other questions? Please don't be shy.
Okay, Professor.
Yes.
Sorry, maybe probably I must have missed it in one of your class, but if graphene does not have a band gap, what's the difference of its conductivity with that of metals?
Oh, well, that's a really good question. The conductivity of graphene looks like conductivity of metals in many aspects, like its dependence on temperature can be similar to those of metals, like you hit the sample, the resistivity goes linearly with T in a wide temperature range, but the dependence of conductivity on carrier density in graphene is different from that in metals. This is because the density of states in graphene is different from the density of states in metal. This comes from two facts. Most metals are three-dimensional, and the dimensionality of metals is different, and most metals have nearly parabolic energy spectrum, and therefore the density of states is also different. If we plot the density of states for like potassium or calcium versus energy, it would look something like this, like square root of energy. And if we could tune the density of metals with some tools, we would see that the density dependence of conductivity in metals is different from the carrier density dependence of conductivity in graphene. But this is quite a fantastic experiment because it is hard to tune the carrier density in bulk metals due to strong screening. So graphene should, in terms of density dependence of conductivity, should be compared only to other semiconductors to be practical, but not with metals. Did I answer a question? Do you have any remaining questions?
Yes. Thank you.
Any other questions regarding the conductivity part? Okay, if no more questions, let's pass to more interesting situations where the kinetic equation allows us to handle the processes of diffusion and heat conduction. The formal trick that can help us to do this is to assume that, for example, if the sample is subjected to temperature gradients, one end of semiconductor is hot, the other one is cold. And for example, if it is subjected to density gradients, at one part of the semiconductor you have induced large electron density, and in the other part it is small. Actually, we can encode it into the equilibrium part of the distribution function. The equilibrium distribution function in non-uniform samples acquires some coordinate dependence. So the temperature can acquire coordinate dependence, and Fermi energy can acquire coordinate dependence. And roughly, temperature governs the average internal energy in semiconductor, and Fermi level, Fermi energy, it encodes the number of particles. So this is responsible for thermal diffusion, and this is responsible for the normal diffusion. Now, if equilibrium part of the distribution function is modified, the kinetic equation should also be modified. We should retain the coordinate-dependent terms in this equation, and we should retain the terms with the space derivatives of distribution function in the left-hand side of the kinetic equation. It is instructive that here in the spatial dependence term we should retain only the equilibrium part of the distribution function. Despite we have assumed that the gradients of Fermi energy and temperature exist, we still assume them to be small. So we drop the terms looking like velocity multiplied by derivative of delta distribution function with respect to the coordinate. So we drop them and we retain only the derivatives of equilibrium distribution function with respect to coordinate. It means that we assume the Fermi energy and temperature to be weakly varying in space. We assume the gradients to be small. This equation is not much more harder than the previous one. We just need to expand this derivative of equilibrium distribution function with respect to the space. So let's do it explicitly. Derivative of distribution function with respect to the coordinate is the derivative of distribution function with respect to Fermi energy multiplied by the derivative of Fermi energy with respect to the coordinate, and plus derivative of distribution function with respect to temperature multiplied by derivative of temperature with respect to the coordinate. It looks good, but the further simplification is possible. Please look at the combination in which Fermi energy and electron energy appear here. They appear in the same situation, but with a different sign. It means that the derivative of distribution function with respect to Fermi energy equals minus the derivative of distribution function with respect to electron energy EP. They appear at the same place but with different signs. It means that the derivatives with respect to the quantities are equal except for the sign. The derivative of distribution function with respect to energy can be also simplified. It can be written as derivative of distribution function with respect to its argument. I call it argument, multiplied by the derivative of the argument with respect to the temperature. But derivative of distribution function with respect to the argument is nothing but the derivative with respect to the energy multiplied by kT. And the derivative of the argument of the distribution function with respect to kT is easily evaluated. It is minus energy reckoned from the Fermi level divided by kT squared. So we have expressed all the derivatives of distribution function with respect to space via gradients of temperature and Fermi energy and derivative of distribution function with respect to energy itself. Now I will try to explain why it is useful. This is useful because we can see some interesting combinations of quantities that indeed make the driving of electrons in semiconductors. To see these combinations, let us finally simplify the term with normal electric force. It is actually the force multiplied by derivative of distribution function with respect to energy multiplied by derivative of energy with respect to momentum. But derivative of energy with respect to momentum is nothing but velocity, and electric force equals nothing but minus EE, or the derivative of electric potential with respect to the coordinate. So we are able to express this term with the driving force also as a derivative of distribution function with respect to energy. Now we see that the diffusive term and the force term look very, very similar. Here the derivative of distribution function with respect to energy, and here it comes again. They can be collected. Here the velocity and here the velocity. They can be collected all together. And we see what indeed causes the driving of electrons in semiconductors is derivative with respect to space of the electric potential energy minus Fermi energy. This quantity has a special name. It is called electrochemical potential. And this electrochemical potential shows us the combined effect of drift and diffusion. And it actually tells us that if electric field is present in the sample, it doesn't necessarily lead to electric current, because actually in practice there could be a counterbalancing dependence of Fermi energy with respect to space that yields us the counter current. Now I would like to ask some questions, some basic physical questions to show that it is important. For example, let us recall the basic physics of p-n junction in semiconductors. Let's take a p sample and n sample. You know that there exists a built-in electric field inside of this sample, which looks like this. So this is the dependence of potential energy with respect to the coordinate. The potential is dependent on the coordinate, so there exists a built-in electric field inside of the sample. But still, if we do not apply an external voltage source, there is no current. Why is there no current in this situation? The electric field exists, but there is no current. Why? you can bring either physical arguments why current should not exist despite the presence of electric force, or you can bring mathematical arguments from what we have written just before.
If we look on the formula, then we can suggest that Fermi levels will be to counterbalance the potential part in the gradient. So there will be no current. And in the physical meaning, there will be a depletion zone, and there will be charges on N and P borders, and these free charges will also counterbalance the current.
Okay, this is a good answer. So from mathematics, you could suggest that that the dependence of Fermi energy with respect to the coordinate would compensate the force term, and it is indeed so, because what is Fermi energy? Fermi energy is the distance between conduction band and the Fermi level, and it is different across the sample. So here, when the conduction band is very close to the Fermi level, the Fermi energy is high, and the density of electrons is strong. So this area is highly enriched with electrons. There are many electrons here, and this area is depleted. There is a very limited number of electrons. So looking at this profile of carrier density, you expect the diffusion flux to be directed from enriched region to the region where the electrons are very limited. So the diffusion flux would be directed to the left, but there should be a counterbalancing flux due to the electric force. And due to electric force, electrons want to get from the mountain, get down from the mountain. And the electric force is directed toward the downhill, and the drift flux, this flux is called drift, would be directed toward the right, from the mountain downhill. These fluxes would exactly compensate each other in the equilibrium. And actually, the quantity that appears here is called quasi-Fermi level, or in brief, it is called Fermi level. So the derivative, what occurs under the derivative is Fermi energy minus potential energy, and it is denoted by a letter F, dF with respect to dr. This is, I think, the most important knowledge, one of the most important knowledge that you should take out of the course. To get finite electric current in semiconductor, you should have the gradient of the Fermi level, which is contributed by gradients in electric potential and gradients in Fermi energy. The Fermi energy can be expressed through the carrier density. So there can be different situations. You can have either uniformly doped semiconductor and electric field. Therefore, it will be a pure drift current. You can have no electric field, but you can have non-uniform carrier density. It would be diffusive current, but they can either coexist and enhance each other, or in some equilibrium situation they can counterbalance each other and yield zero, like we have considered in a PN junction. Just to remind you some simple life situations, I don't remember, maybe I have already asked this beautiful question, why despite the action of gravity force on all the gas molecules in our atmosphere, all the gas molecules don't fall on the surface of the Earth. Because there is force, gravity acting on these molecules, they should fall eventually down. Why doesn't it happen? Now you can answer it knowing the kinetic equation. No? I think I did it in one of my previous lectures. This is a beautiful question about kinetic theory. Gravity is acting on all the molecules in the atmosphere, and they should fall down on the Earth's surface, but they do not do it. Why it happens? Oh, you are confused. It's great.
Maybe the gradient of the distribution function causes the drift of the particles to updrift.
Yeah, that's a correct answer, but more precisely, it is called not the updrift, but the diffusion. So if you plot the distribution function of molecules with respect to energy, which is nothing but mgh, then it would be a decaying exponential. It will be a Boltzmann distribution function. So we have mg force acting downwards, but we have lower and lower density of molecules as we go up in the atmosphere. So the diffusive flux, which is proportional to the gradient of the Fermi energy and actually to the gradient of molecule density, is directed upwards. Actually, this is exactly this compensation that is seen in the Boltzmann kinetic equation. The force term, due to the gradient of potential energy in the gravity field of Earth, is exactly compensated by gradient of carrier density, and we have no overall motion of the gas molecules. So these examples of compensation in our life are ubiquitous and seen very often. Any questions here? Because if no questions yet, we will pass to the calculations. Just a hint for account of diffusion. To calculate diffusion in semiconductors, we do not need to solve the equation again, because if we have solved the kinetic equation in the presence of electric field, in the presence of electric potential gradients, dE by dr, when we have you have non-uniform density in the sample, you just make a replacement. You replace this gradient of electric potential by the gradient of electrochemical potential, or by the gradient of the Fermi level with respect to the coordinate. What you do this way, you automatically include diffusion into your consideration. If you know the conductivity, you automatically know the diffusivity. If you know the mobility, you automatically know the diffusion coefficient. It is actually Einstein's rule for diffusion and mobility. Diffusion coefficient would be equal to KT multiplied by mobility mu. This is the rule that you would eventually obtain when trying to get diffusive characteristics from electrical characteristics. Well, before going to considerations of thermoelectric phenomena, I would like to give a picture. I would like to stress once more why diffusion and drift can compensate each other, and I will try to illustrate some concept in semiconductors like Fermi energy and Fermi level on our natural examples. The potential energy in semiconductor of electron in semiconductor, which is minus the elementary charge multiplied by electric potential, can be sometimes associated with the bottoms of ponds or lakes, water reservoirs, which can vary in space. The Fermi energy can be associated with the local amount of water, local height of the water in this pond or lake. And the Fermi level, which is Fermi energy minus Eφ, well, according to this formula, it yields nothing but the constant level of top water. So the top water level is equivalent to the, in natural water reservoirs, is equivalent to the Fermi level in semiconductors. And you see here the nice situation where the water is steady despite the fact that the local height of the bottom is varying and the local height of the water is varying, but they are varying simultaneously, so that the Fermi level or the top water level remains constant, and there is no overall flux of the water in this pond. And there can be different situations. These different situations in semiconductors can also have water analogies, like you can consider a dam on the river, and this picture with the dam illustrates two types of flux. For example, here the electric potential phi, the potential level phi left equals to the potential level phi right. In terms of mechanics, the heights of the bottom are equivalent here, so the potential energies are equivalent here, but the heights of the water are different, so there is a general water flux from the left to the right. So here height at the left is not equal to the height at the right, and it is equivalent to the presence of diffusive flux in semiconductors. You can associate these heights with Fermi energies, EFL and EFR. They are not equal to each other, so you can expect overall diffusion from left to the right. The comparison of left and right parts of the figure gives us the illustration of diffusive current in semiconductor. But we can also look at the middle. What happens in the middle is varying bottom of the water reservoir. So the height of the bottom, each bottom is varying here, but the local width of the tube is constant. W with number 1 equals with number 2 equals with number 3. Here we have a purely drift flux due to the change in the potential energy, but by holding the height, the local amount of water the same. So what happens here is drift, and what happens between left and right parts of the sample is the diffusion. So actually in many situations in semiconductors, especially when analyzing the operation of devices with non-uniform doping, you will need to evaluate the, you will need to plot the potential energy diagrams and simultaneously show the variations of carrier concentration with changing Fermi energy. This would be very important if you will be willing to be a professional in the semiconductor electronics. Now we have quite little time left, but I would like to sketch what we will do in the next lecture with the phenomena in the presence of temperature gradient, with the thermoelectric phenomena. We will be willing to find the electric current in the presence of the temperature gradient. The presence of temperature gradients is more complicated compared to the case of Fermi energy gradients, because near the temperature gradient we get an extra energy dependent term, energy reckoned from the Fermi energy. This makes this simple absorption of gradients into the of temperature gradients into the gradient of electric field impossible. What was possible for the diffusion becomes impossible for thermodiffusion. But still the solution for the kinetic equation is straightforward here. You write the correction to the distribution function delta F as minus momentum relaxation time multiplied by everything what we have on the left. Vp gradient of temperature multiplied by derivative of distribution function with respect to energy multiplied by energy reckoned from the Fermi energy divided by kT squared and minus something like drift and diffusion terms that we will be not interested in anymore. So the solution for the distribution function in the presence of temperature gradients is obtained, and we can also now evaluate the flux, the average electric current due to this amendment delta F. It equals the sum over momentum space of Vp multiplied by the obtained distribution function delta F. So again, we will need to evaluate some integrals that would be slightly different from the integrals that we had in the case of electric conductivity, because they would involve this difference of energy and Fermi level. I would like to make a short speculation before evaluating the integrals. The speculation having some physical backgrounds and explaining why thermoelectric currents are weaker than electric currents if gradient of kT, for example, is of the same order that the gradient of potential energy. The thermoelectric current, at least in metals, would be much weaker than electric current. So temperature doesn't induce such strong driving of electric current than in comparison with pure electric field. To explain this, we can make the following interesting, the following picture. We can consider a metal or degenerately doped semiconductor, one of the ends of which is hot and the other end of which is cold. This is the coordinate. Actually, the charge carriers would diffuse from the cold end to from the hot end to the cold end. Let's try to see it as a flux in terms of distribution function. The distribution function at the hot end is highly smeared Fermi function. The distribution function at the cold end is abrupt Fermi function. Let us call the extra amount of charge carriers above the Fermi levels as electrons. Well, it might look that everything is electrons, but what we call below the Fermi level, the empty spaces below the Fermi level, we would call holes. It's like a more notation of Fermi liquid theory, but anyway, we can do this. Empty places before the Fermi level would be called hole. They have effective positive charge. Occupied spaces above the Fermi level would be called electrons. So we would see that there are many electrons at the hot end and many holes at the hot end. And there is 0 electrons at hot end and 0 holes at the cold end. So both electrons and holes would make diffusion from hot end to the cold end, and both would make flux from left to the right. But what about charge flux? Electrons have negative charge minus E modulus, and holes have positive charge plus E modulus. Their charges would almost compensate each other, and there would be particle flow, but there would be no charge flow, and electric current JQ would approach 0, approach with some subtleties. The subtleties are the following. Actually, high energy electrons and low energy holes can have different momentum relaxation time depending on the type of scattering. And high energy electrons typically have large density of states and large average velocity, because velocity is proportional to the square root of energy. And holes have low density of states and low velocity. And typically, electron flux overwhelms the hole flux. So typically the electrons, the average direction of flux in metals is that electrons move from hot to the cold, and the flux of electrons is higher than the flux of holes, and the direction of the electric current is oppositely from cold to the hot. We will see further on the next lecture that this sign alternating term, E minus EF, is responsible for almost complete compensation of electron current above the Fermi surface and hole current below the Fermi surface. Actually, when we evaluated the conductivity, we evaluated the average of sign non-alternating function. And when we evaluate the thermal diffusion coefficient, we will take an integral of sign alternating function, and the integral of the sign alternating function would be generally small. But it is small, but it's still observable and measurable in many experiments. To conclude my lecture, I would like to say that evaluation of thermoelectric phenomena is very important for the operation of thermoelectric energy generators, and if in some place you can accommodate an engine between hot and cold ends, you can take a p-n junction. Both electrons and holes would diffuse from hot to the cold, but if you connect it in the following way, there would be a general electric current from pointing to the direction of the whole current. So the evaluation of thermoelectric phenomena is important for the construction of thermoelectric engines based on semiconductors, and important for the reverse process of thermoelectric cooling. With that, I would like to finish my lecture.